Hello there, welcome back. This is Chapter 9, Magnetism and Electromagnetic Induction, out of our Conceptual Physical Science book. Let's get started. So in this lecture, we're going to help you to understand about magnetic poles and fields and domains. We'll get into that in a minute. And electrical currents and magnetic fields and how they're related. Magnetic forces on a moving charge. Electromagnetic induction. Generators and AC or alternating current, power production, what the transformer does in boosting or lowering voltage, and field induction. So we're starting to get into some more modern physics here. So magnetic poles, you've seen a magnet before, and you can't have one pole without the other. We have a north pole and a south pole, and they're related. And this even goes for the Earth too. We have a north pole and a south pole magnetically. So there's no one single pole known to exist. And so we have this bar magnet here, and the poles are different at the ends. So the magnetic force is a force of attraction or repulsion between a pair of magnets, which depends on which end of the magnet is held near the other. And the behavior is similar to electrical forces. They act in the same way. And so the interaction strength depends on the distance between the two magnets. And so magnetic poles also give a rise to magnetic force. And the two types that interact with each other are either a north-seeking pole or a south-seeking pole. And so like poles repel and opposite poles attract. Maybe you've done this when you were in school, when you were a child. You had two magnets, and you try to push a north and a north pole together. You can't almost even make the magnets touch, depending on how strong they are. They repel each other. Whereas you put a north and a south together, they click really quick. And so magnetic fields occupy the space around the magnet and are produced by moving electrical charges. And so there's a field shape that you see here. The spread from one pole curves around the magnet and returns to the other pole. And the closer these field lines are together, the stronger the strength of the field is. And so these fields are produced by two kinds of electron motion. Remember, the electron goes around the nucleus in the atom. And so there's an electrical spin with a main contributor to magnetism. A pair of electrons is spinning in the same direction and creates a stronger magnet. We can also do this with electron revolution when it goes around the atom. And so electrical currents and magnetic fields are related and they're connected. A magnetic field forms a pattern of concentric circles around a current carrying wire. And there's a thing here you might want to look up on Google called the right-hand rule about how they interact. So if I hold my thumb like this on my right hand, the field lines are going to curve around counterclockwise to that. Now when the current reverses direction, the direction of the field lines reverse, and we'll get the opposite of that. So here we see a magnetic field intensity curve. Increases the number of loops, increasing the current carrying coil. So the more magnetic field lines of coil there is, the more magnetic field there's going to be, the more current there is. Now, if you send a current through a magnetic field, charged particles will move in that field and get a deflecting force on them. This is greatest when they move at right angles to those magnetic field lines. Now, we don't have this in the United States, but in Japan they have trains that are magnetically levitated. And how does this work? Well, when an upward magnetic force is greater than gravity, an object can levitate. A magnetically levitated vehicle is shown on the right there. They call it a magplane. There's no friction, no vibrations. Now, how does a magnetic force work in space? Well, the Earth has a magnetic field. Any object in space with a liquid iron core will generate a magnetic field, and that's called the dynamo effect. And so Earth's magnetic field deflects many of the charged particles that make up the cosmic radiation. This is a really good thing because it helps us keep the electrons away from endangering the Earth's infrastructure. When we have a breakdown of the magnetic field lines, the sun's photons can interact with the electrical grid on the Earth and cause blackouts. Now, an electrical meter does detect electrical current, and examples of this would be a magnetic compass or a compass and a coil of wires. We can look at the force on moving charges with a galvanometer. And the electric motor is also induced by a magnetic force on moving charges. And so each time the coil makes a half rotation, as you see in the diagram here, the direction of the current changes in a cyclic fashion to produce continuous rotation, and that produces a current. In electromagnetic induction, this was discovered by Faraday and Henry, and the voltage is induced with a change of a magnetic field strength in a coil of wire. And so we see here the magnet being put through the coils, inducing that. And so the induced voltage can be increased by increasing the number of loops on the wire in a coil, or increasing the speed of a magnet going through the coil. Rapid motion creates the greatest voltage. And so the induction will occur whether the magnetic field lines move past the wire or if the wire moves through the field lines itself. You'll still get induction. More loops in the coil, more induction. And so now we come to Faraday's law. And Faraday's law states this: the induced voltage in a coil is proportional to the number of loops multiplied by the rate at which the magnetic field changes within those loops. And so the amount of current produced by electromagnetic induction is dependent on, again, the resistance of the coil, the circuit that it connects, and the induced voltage in the coil. So it is more difficult to push a magnet into a coil with a lot of loops, many loops, because the magnetic field of each current loop resists the motion of that magnet. And this brings us to a generator and alternating current, which we get from the plugs in our homes. It's the opposite of a motor. It converts mechanical energy into electrical energy versus a coil motion, and produces AC current and alternating voltage. Now, how do we produce power? We use Faraday's and Henry's discovery of electromagnetic induction. Nikola Tesla and George Westinghouse showed that electricity could be generated in sufficient quantities to light cities. And this brings us to the transformer, which we have on our electrical grid. So we have an input coil wire, primarily powered by AC voltage source. We have an output coil wire, the secondary connected to the external circuit. And so we wound this on a common iron core. Magnetic field passes through it, and AC in one coil induces AC in the second coil. And so we see these transformers everywhere. The common transformer lowers 120 volts coming out of the power grid on the wall to 6 or 9 volt. It also converts AC to direct current by means of a diode inside. And in the common neighborhood, the transformer usually steps down a lot more voltage, 2400 volts down to 240 volts. And so this brings us to the equation for electrical power. It is voltage times current. And so the electrical grid in cities uses transformers. The voltage generated in power stations is stepped up with transformers prior to being transferred across the country by overhead cables. And then the other transformers reduce the voltage or step down before supplying it to homes, offices, and factories. And so the electrical field induction is a basic to electric field induction is that the current and magnetic fields can induce each other. An electrical field is induced in any region of space in which a magnetic field is changing with time, or a magnetic field is induced with any region of space in which an electric field is changing with time. And finally, light is produced by the mutual induction of electrical and magnetic fields. The speed of light is the speed of illumination of these fields. If it's too slow, the fields will die out. If it's too fast, the fields build up a crescendo of increasing energy. And at the speed of light, which we call the constant little c, is just right, and there is light. And that's all for chapter 9.